Okay, in this video, we're going to continue our discussion of confidence intervals with sample proportions. So let's go ahead and dive right in. So a recent survey found that 74% of 1,644 randomly sampled first-year college students returned to college the next year. We're then asked to estimate the national first-year student retention rate. So first, we're asked to check the assumptions and conditions are met for the inference on the proportions. And what we are looking for is to check if we can use a normal distribution here. So in question A here, we're told that they are randomly sampled. So random, yes. Independent, yes. Is it less than 10% of the total population? Well, 1,644 first-year students is certainly less than 10% of the population of first-year students across the country. So less than 10% of population. Yes. And then we have our success-failure condition. Success-failure. And remember that we need n times p greater than or equal to 10 and n times q greater than or equal to 10. Well, in this case, we have an n of 1,644 times a p of 0.74. Well, this is equal to 1,217 and n times q, so 1,644 times 0.26, which is equal to 427. So, yes, our success failure condition is met. So we can go ahead and assume a normal distribution on this, which will help us. We're then asked to construct a 98% confidence interval. So B. And we remember that the equation for a confidence interval is equal to p hat plus or minus our margin of error, where our margin of error is equal to z star times the standard error of the proportion of our sample. We have some information that's given to us in our question that's going to help us. So our value of p hat is equal to 0.74, which means our value for q is equal to 1 minus p hat, which is equal to 1 minus 0.74, which is equal to 0.26, and our value for n is equal to 1,644. 1,644. That looks like an 8, so let's just rewrite that. 1,644. So let's go ahead and write out our confidence interval here. So our estimate here is 0.74 plus or minus our z star. We will come back to that in a second. At our standard error of p hat, well, we remember that our standard error of p hat is equal to the square root of p hat times q hat divided by n. So times p hat q hat divided by n. So 0.74 plus or minus z star times the square root of 0.74 times 0.26 divided by 1,644. So we can go ahead and do this math. So 0.74 plus or minus z star. Again, I promise we will come back to that. So 0.74 times 0.26. So is equal to 0.1924 divided by 1644. Gives us again a very small number, so we won't punch in that step. So 0.74 plus or minus z star times the square root of that value, 0.01082. We'll just round to 5 decimal points there. So now we're tasked with finding what is our z star value for our 98% confidence interval. So let's go ahead and just visualize our normal distribution for which we said we could apply here. Again, our standard normal curve is centered around 0. And what we're looking for is that region where 98%, which means that we have a value of 0.01 and 0.01 in each of our tails, right? So if we're looking at this, we're saying we could look at this value right here. We'll just label this x. So we're going to say the probability that z is greater than or equal to x is equal to 1 minus the probability that z is less than or equal to x. And what's the probability that z is less than or equal to x? Well, what we're looking for here is the probability to the left, which is going to be equal to 0.99000. Okay, so that's the z star value that we're looking for, an area to the left of 0.99000. So let's go to our z table, and we can just erase some of these previous markings here. And we're looking for 0.9900. So what we have is we have a value that's going to be somewhere between these two values right here. And we can probably make this a little bit neater. Right here. So somewhere between the values of 2.32 and 2.33 gives us a probability to the left of 0.990. Now, to the extent that we have 0.99010, let's just go ahead and use 2.33 as our critical value. Now, given the luxury of computation, you could find a more precise value. And if you were to type that in, the more precise value is actually 2.326. But for the sake of this example, we're just going to use this value right here of 2.33. So that means that 0.74 plus or minus 2.33 times 0.01082. So 2.33 times 0.01082. So 0.74 plus or minus 0.0248. And again, we'll keep this to 5 decimal points, and we can store this value. So what we get is 0.74 minus 0.02489, which gives us here a value of 0.7151. And then we get 0.74 plus 0.02489, which gives us a value of 0.7649. Again, rounding to 4 decimal points there. So what do we have is that we have our 98% confidence interval. So this would mean we're 98% confident that the true proportion lies somewhere between 0.7151 and 0.7649. Now we're not done with this question. We have a couple of other parts to this. So question C, what would the effect on the width of the confidence interval be if the sample size were increased by 44%? So we'll just make a little note here to our draft. So if n is increased by 44%, so we recall that our equation of our confidence interval is equal to our estimate plus or minus our z-score times the standard error of the proportion of our sample, which is also equal to p hat plus or minus z star times the square root of p hat times q hat divided by n. Now, importantly, the size of the sample matters in this equation. So if we are increasing our sample size by 44%, we are going to change the size of our standard error, which we then can infer that it's going to change our confidence interval. Or a better way of saying that is it will change our margin of error. Remembering that our margin of error is this part of the equation right here, our z star times our standard error of p hat. So if n was originally, what was our original sample size of n was 1644, and we're going to increase it by 44%, we're going to say times 1.44. This will increase it by 44%. So 1644 times 1.44 gives us a new value of 2,367.36. We'll just keep it as 2,367 people. So from there, we can adjust our equation. So we know that our estimate is 0.74 plus or minus our z-score, which we've calculated up here to be 2.33 times 0.74 times 0.26 divided by our new sample size, which is 2,367. So let's go ahead and punch that into our calculator. So 0.76 times 0.26 divided by 2,367. Take the square root of that value. So what we get here is 0.74 plus or minus 2.33 times 0.0093 0.00913, and we'll just keep it to that value. Kind of 6 or 7 decimal points there. Oh, what the heck? Let's do a few more. 3, 6, 8. So we're then going to use that value. So 2.33 times this value gives us 0.74 plus or minus 0.021289. So 0.021289. And then we're going to do 0.74 minus this value, which will give us 0.7187. And then 0.74 plus this value, which gives us 0.761289. So that is our new confidence interval when we increase our sample size by 44%. Now, what do you notice about the difference between these two confidence intervals? This one that we calculated with a sample size of 1,644 and this one that we calculated with the sample size of 2,367. Well, you'll notice that the numbers are, relatively similar. But what you will notice is that the confidence interval for the larger sample size, that is this one right here, is actually smaller. It's narrower. And if you were to take the difference between them, so 0.7649 minus 0.7151, you would get the distance between the two values. And similarly, you could do the same down here with this confidence interval right here. So why don't we just do that? So we'll calculate the distance, the delta here, 0.7649 minus 0.7151 gives us a delta of 0.0498. And we can calculate the delta right here. So 0.761289 minus 0.7187 gives us a delta of 0.0426. So what you'll notice is that 0.0426 is less than 0.0498. In other words, the confidence interval is smaller. And this is because as we increase our sample size, our standard error gets smaller, and as a result, our margin of error gets smaller. So overall, our confidence interval becomes smaller. And then finally, we have this last part here. So what would happen if the confidence interval was reduced from 98 to 95%? So if Z star, we have to look at our Z star value here. So 0.74 plus or minus our Z star times our standard error. And this is our original standard error in our question of 0.01082. 0.01082. That's the standard error that we calculated in part 1 of this question. So let's look up our confidence interval for a 95% confidence interval. So we're going to look up our Z star value. So what we're going to look up is the area to the left of 0.75. So we look up that value and we see that right here, exactly at 1.96. So our Z star for our 95% confidence interval is equal to 1.96. So 0.74 plus or minus 1.96 times 0.01082. And just a reminder, the standard error of the proportion of our sample was equal to the square root of 0.74 times 0.26 divided by 1644, which gave us our standard error of 0.01082, which is seen right here. So 1.96 times 0.01082. So this gives us a value then of 0.74 plus or minus 0.02121. So then our 95% confidence interval is 0.74 minus alpha A gives us 0.7189. We'll just call this 0.7188, and 0.74 plus alpha A gives us 0.7612. So this is our new confidence interval at a 95% confidence interval. And that will do it for this video. That's it for this video, but if you found that it helped to make statistics easy, consider showing your support by giving the video a like. And if you still need more help with statistics, then consider subscribing to the channel if you haven't already. I look forward to solving many more problems with you next time.